So, welcome again. I think it's time that we start with the second topic of today's work. So it will be about polymer synthesis, and the presentation will come by Professor Irena.
Thank you, Ramiro, for the introduction. Hello, everyone. From my side, I'm Irena Pulka from Faculty of Polymer Technology College. In this morning session, we heard a lot about polymers, their properties, but in this lecture, I will talk about polymer synthesis. Mainly I will talk about chain polymerization and step-road polymerization. In chain polymerization, I will focus on radical chain polymerization. But for the beginning, maybe a question for you. Do you have any experience with polymer synthesis?
In theory.
Only in theory. Okay.
Something with polyaniline, but that's...
Yeah, something small with polymer.
Okay. Do you have
Long.
Okay, yeah. Because in this afternoon we will go to the lab and prepare some polymers in the laboratory. Yeah. So traditionally, polymers have been classified into these two groups: additional polymers and condensation polymers. This classification was based on the atoms that are present in monomer and atoms that are then present in the repeating unit of the polymer. So if the atoms are the same, we talk about additional polymers. If the atoms are not the same, we talk about condensation polymers. But if we have a look on this polyester synthesis, so it could be prepared from lactone, or from hydroxycarboxylic acid. So in the first case, we don't have any side product, so that the atoms are the same in monomer as in repeating unit. But in the second case, we have a side product, so the atoms are not the same. So to avoid this ambiguity, polymerization are nowadays more commonly polymers are nowadays more commonly classified according to the polymerization mechanism. So that's why we talk about chain polymerization and step-growth polymerization. So if length of the polymer increases by linking of one monomer unit at the end of the growing chain, we talk about chain polymerization. So if the polymer length and molecular weight increases in a step manner, then we talk about step-growth polymerization. And that are these two types of polymerization I'm going to talk about today. So if we start with chain polymerization. Chain polymerization could be initiated with radicals. It could be ionic polymerization, chain polymerization, ring company chain polymerization, and also coordinated polymerization. But today I will mostly focus on radical polymerization. So for the beginning, let's have a look on this animation video on chain polymerization, and at the end we will watch this video again, and you will be familiar with all parts of chain polymerization. So let's have a look. Let's initiator this molecule here. Okay, that's a short video, short animation. So radical chain polymerization is characteristic for vinyl group. So for molecules with a double bond. And from the commercial point of view, this group, in this group of polymers are polymers that are produced and processed in very high quantities, like polyethylene, polypropylene, polystyrene, polyvinyl chloride, polyethylene methacrylate, and that are actually polymers that we use more or less on daily basis. And on this slide are these polymers with resin identification code. So 1 for polyethylene terephthalate, 2 for polyethylene, 3 for polyvinyl chloride, 4 for low density polyethylene, 5 for polypropylene, and 6 for polystyrene. And all these polymers, except polyethylene terephthalate, are produced with chain polymerization. So on the upper part of this slide, you have monomer units, and on this lower part, you have repeating units of the polymers. And as we can see here, almost, actually in all cases, we have in this backbone carbon atoms. And now one question for you. You can scan this QR code and but I will send you the link to the questionnaire in chat. And what is right answer? What is common to the monomers used for chain polymerization? Sorry? Double, yeah, double bond, but also C and hydrogen. It's yeah. So OH and COOH groups are more common in step rod polymerization, but still we can have these groups here as well, but are not so characteristic. Yeah. Okay. Okay. Yeah. So again, I have the same problems as you before. Okay. Okay. Yeah. Now we are. So double bond is characteristic for monomers that are used for chain polymerization. And these double bonds, they consist of one P and one sigma bond. And this P bond of the monomer can be ruptured in the presence of heat. So it means if we during the transport or during the storage, this P bond can be ruptured, and two-headed free radical can be formed, and this radical can start polymerization as well. But of course, that is polymerization we don't want. So that's the reason why inhibitors are added to the monomers to prevent polymerization during transport or storage. And but these inhibitors should be removed before we start the polymerization, or we should add some more initiators to overcome these inhibitors. Yeah, and now we will start with the steps of chain polymerization. So chain polymerization is a reaction that can be typically divided into 3 stages. The first stage is initiation, the second stage is propagation, and the last stage is termination. Initiation is formation of initial reactive center and the reaction of this reactive center with monomer. These 2 reactions are part of initiation. Propagation is chain growing, so by adding separate monomer units at the end of the growing polymer chain. And of course, termination is the final reaction that eliminates a reactive center. But due to the speed of individual propagation reaction, polymer chains are generated very rapidly. So if we stop polymerization after, for instance, 1% of conversion of monomer to polymer, in the reaction mixture, we already have polymers with final molecular weight. And of course, at the end of the reaction, we have higher quantities of these polymers, but regarding molecular weight, there is no big change. So let's have a look at this individual step in more detail. So in the first initiation step, initiators are very important because they start polymerization. So initiators are molecules that decompose and create radicals. In the case we talk about radical polymerization, and this the composition of initiators could be due heat, UV, electricity, or due to redox reactions. So we talk about thermal initiators, photochemical initiators, and redox initiators. And let's have a look on these separate initiators. At first, thermal initiators. So thermal initiators decompose to radicals when they are heated. Most commonly, very often we use peroxides or dinitriles or azo compounds as thermal initiators. And dinitriles or azo compounds like azoisobutyronitril, that's this molecule, require temperature about 70 to 80 degrees to decompose and to form radicals. While peroxides like benzoyl peroxide is in this group, require temperature in the range of 60 to 140 degrees to decompose and form radicals. Here is a typical equation for the situation of benzoyl peroxide and azoisobutyronitril. And if we look at benzoyl peroxide, at the first stage, benzoyl peroxide breaks and two free radicals, benzoyl radicals are formed, but these benzoyl radicals can breaks down further to create phenyl radicals, And about initiators, it should be also pointed out that because of recombination and because of side reactions, not all radicals that are formed are involved in polymerization process because of these side reactions and recombinations. So that's why initiator efficiency is employed. So initiator efficiency could be around 0.7. So it means that 70% of radicals produced are involved in polymerization process. And the rate of the composition of initiator usually follows first order kinetics, and of course is dependent on the solvent that is used and on the temperature. For some initiators, here are half-life time at the different temperatures. For instance, for azobisisobutyronitril, half-life time at 50 degrees is 73 hours, at 70 degrees is 6.1 hours, and at 100 degrees it's 7.2 minutes. So for other initiators, of course, this half-life time is slightly different, but general rule is that at higher temperature, this half-life time is shorter. So that's about thermal initiators. So let's move to the photoinitiators. Photoinitiators are initiators that decompose under the presence of UV or visible light. So the advantage of using photoinitiator is that polymerization can take place at room temperature. So, for instance, if we deal with systems or monomers that are thermally not stable, then we should not heat this mixture or whatever we have. And in this case, we can use photoinitiators. So as we have seen on one of the previous slides, the initiation is a two-step process. Radical generation and reaction of this radical with monomer. And the same is with photoinitiator. But of course, here we have some other factors that affects the composition of initiator, and of course, very important is light source. So the intensity of this light and wavelength of the light. And here is a list of some common photoinitiators. In the lab today afternoon, and I think on Wednesday as well, you will use IRPACURE 184. That's commonly used photoinitiator, and we quite often use also this one, IRPACURE 1173. So here I have two more initiators that were not listed in the previous slides, and on the the first structures are structures of initiator, and these two structures are structures of radicals after decomposition. So, and researchers at the Institute of Physical and Theoretical Chemistry in Graz have prepared simulations of radical generation rates. And this graph represents this simulation. And as we can see, the blue line is for IRPACURE 1173 under this low-powered LED. This initiator didn't form radicals, didn't decompose and form radicals, but the IRPACURE 189 did decompose and form radicals, and the speed of formation of radicals is rather fast, especially in comparison with thermal initiators. So in this case, we can speak about seconds to form radicals. Yeah, the next slide. So we use photoinitiators in combination with oligomers and polymers in nail polish formulations. Yeah. So after exposure of this formulation to UV light, monomers and oligomers start to polymerize, and this film gets hard, but not on the top. The top layer remains sticky and unreacted. That's because of oxygen inhibition of upper layer. Yeah, and this layer has to be then removed. Yeah. Yeah, that's use of photoinitiator in our everyday life. And the last group of initiators I will mention today are redox initiators. Redox initiation is a method of generating free radicals by one electron transfer reactions between the oxidant and the reductant. And these systems are very often used in water media. So for in emulsion systems, usually lower temperatures. So as mentioned, this initiation step is composed of these two reactions. So initiator decomposition interaction with monomers. So this part till now was in initiator decomposition, and next part is reaction of these radicals with monomer. So on this slide, both reactions are presented on a sample of benzoyl peroxide that decomposes to a benzoyl radical, and reaction of this radical with styrene. And that's how this first monomeric radical is produced. Yeah. And so these two reactions are the first part of polymerization. But also in this this addition of styrene to the radical happen in two ways. So the radical can be attached at the methylene group, not directly attached to the phenyl group, that's this one, or to the methylene group that is directly attached to the phenyl group. So there are two possibilities, but this addition overwhelmingly occurs on the methylene that is not directly attached to the phenyl group. That's because the unpaired electron can take part in resonance with the phenyl group, and also steric factors favor this addition. So because of these two reasons, we usually have for formulations at the end that favors head-to-tail polymer chain structure, as we already seen. Yeah, as we already seen before by Professor Kusic. Yeah, so that's addition of monomer. Yeah, and it's the same for the whole propagation. So for all monomers that are added, always this addition is to the methylene that is not directly attached to the phenyl group. So that's why we have this head-tail structure. So as mentioned already, this propagation step is growing of the polymer molecular weight by adding monomer units to the growing chain. And this reaction is very fast. So that's why we have high molecular weight already at the beginning of the reaction. And as mentioned, termination is end of this, the last step of this reaction. and termination can happen in two ways, with a combination or with disproportionation. Combination is just coupling of two radicals, while disproportionation involves hydrogen and chain transfer. And in this case, two polymers are obtained. One is saturated and the other one is not saturated, but only the last monomer has double bond. All other bonds in these polymer chains are single bonds. Okay. Again, there will be one question, but yeah, you can answer it, and I will tell you results. So, what is the rate determining step of radical polymerization? So till now there are 7 responses. First answer for the first options is one answer, is one decided first option, 2 the second, 3 the third, and 1 fourth. And Miro, how will you comment?
Very good.
And what is your answer? As I mentioned during my presentation, that the composition of initiator is low. So the rate determining step is initiator decomposition. Yeah. Okay. Yeah. And here I have. that's about chain polymerization, and in the following slides, I will tell you a few things about step growth polymerization. So this term stepwise or step growth polymerization refers to the polymerization in which polymer molecules weight increases in a slow stepwise manner. So at the beginning we have only monomer. Then after certain time, all monomers are reacted. But still, at this point, we don't have high molecular masses because we have only dimers, trimers, pentamers, and higher mers. Only at the end of polymerization, we can obtain high molecular masses because both reactive groups on the monomer has to be reacted to obtain high molecular masses. On previous slides, in chain polymerization, we have mechanism that is more or less or is very similar to all polymers that are prepared by chain polymerization. In polycondensation process, in polycondensation mechanism, we don't have such a process, but it's more or less the same as those proposed in organic chemistry of smaller molecules. Because in this step growth polymerization, we have reactive groups are present, and these reactive groups have to react. So that we can talk about monomer that is used in polycondensation process. This monomer should have or has to have two functional groups. So, for instance, like two acid groups or two OH groups. In this case, we obtain polymer with ester, so obtain polyester. But what happens if we have compound that has only one functional group in our mixture? Sorry, it means if we have such a molecule in our mixture, it means that polymerization stops. So in step growth polymerization, the purity of the monomers is very important, much more than in addition polymerization. And one of important group of polymers that is prepared with step growth polymerization are polyesters. And polyethylene terephthalate is one of them. Polyethylene terephthalate can be prepared with on two ways, so with at least on two ways, with polyesterification and polycondensation. In the first case of polyesterification, ethylene glycol and dimethylene terephthalate is used as a monomer, and methanol is produced as a side product. And of course, this side product has to be removed during during polymerization. And the other way of synthesizing polyethylene tetralate is polycondensation using terephthalic acid and ethylene glycol. In this case, water is produced as a side product. And of course, if you want to obtain high molecular masses, also water has to be removed. It means that these reactions are performed under vacuum. Just to accept. And polyethylene terephthalate is employed as both as plastic for making objects as bottles and as a fiber for making clothing, rugs, and other materials. And that PET is not so easy to mold because it has rather high melting temperature, around 240 degrees Celsius. It also crystallizes relatively slowly, so some extra care must be taken to ensure that PET molded products are fully crystallized, because partly crystallized products, so these partly crystallized parts of the product are prone to cracking, shrinking, and so on. And that's why also nucleating agents and crystallization accelerators are used to improve crystallization rate. And crystallization of polyester resins can be achieved through heating to about 190 degrees Celsius, followed by slow cooling. This rapid cooling is called quenching, and products are more amorphous. This produces more amorphous materials from which these transparent films can be made. And this film strength is increased through application of heat and cooling of the film. And as I mentioned previously, PET is used as fibers, and fibers are produced if molten polymer is pushed through a small hole. So let's have a look on the video. Let's watch this video to see how this is done. So that's how fibers are produced. The next group of polymers are polyamides, nylons. So these polymers are prepared by separate polymerization between molecules containing amine groups and molecules containing acid group or acid chloride group. So acid chloride is more reactive than this acid group. And today in the lab, we will prepare nylon using acid chloride. So side products, we obtain side products in both cases. In one, water is a side product, and in a case of acid chloride as a monomer, hydrogen chloride is produced as a side product. So the name of nylon is nylon 6,6 in this case. And the first digit represents the number of carbons in amine, and the second digit represents the number of carbons in acid in this acid molecule or in acid chloride. So again, I have one question for you. What's the name of polymer with repeating unit shown on the picture? But this, but the picture is on the next slide or in this questionnaire. So I will just send this question or put it in chat. Then we will just go. Okay, answer the question. Yeah. As I mentioned, nylon are named by the number of carbons on in repeating unit or in monomers. So the first digit represents the number of carbon in amine. So in this case, this is 4 and 10. Yeah. So nylon 410. Yeah. But there is another nylon. What's the name of this? Of this part?
We don't see the end.
No, that's the end. Yeah, actually, yeah, it's the end. Sorry, it's not, but here is the end.
5 to 6. It's just 6.
It's just 6. Yeah, exactly.
It's only one.
Yeah. You're right. It's just 6 because in this case we have a monomer like this. So NH2 and COO. So just one monomer with 2 different functional groups. Yeah, that's 9 and 6. Yeah, and that's monomer in this case to synthesize 9 and 6. So its monomer is called caprolactam in this case, and this polymerization is there is a company in Slovenia that produces nylon 6 from caprolactam. They are in Ljubljana. Okay. And important amines are also amines with this 6-membered rings in the structure. So with commercial names Kevlar and Nomex. Kevlar is used for making high-strength fibers that can be used for body armor, bulletproof vests, and for some, for instance, athletic equipment. And on the other side, Nomex has very similar structure, just different site of attachment of functional group. And these two polymers at the end, they have rather different properties. So Nomex is used in clothes for firefighters because it's high thermally stable and not flammable. And let's see let's watch a video, Nomex in comparison with copy. The next group are polycarbonates, so that are polymers with carbonate linkages. And polycarbonate is prepared, in this case, polycarbonate is prepared from bisphenol A and phosgene. This material is optically transparent polymer, and hydrogen chloride is formed as a byproduct. Maybe do you know one product that is where polycarbonate is used?
Sure, we know, but we can know.
Yeah. Well, okay, there are many applications. Okay. It's pretty clear. Sorry, windows, bulletproof glass, and cities, but also for bottles for kids.
Yes.
Yeah, bottles for kids. But there is a concern about bisphenol A to be neural and behavior to make neural and behavior changes in infants and children. That's why polycarbonates, including prepared from bisphenol A, are not allowed to use anymore for baby bottles. For bottles for babies. We are going back to glass or other polyesters that are with similar properties than polyacrylate. And also, yeah, as mentioned, it's used for windows, for bulletproof glass, and for cities, if you remember it.
Yes. They're that generation.
Yeah, and here I have another to see where polycarbonate is used. The next group are polyurethanes. Polyurethanes are a family of materials that are produced from polyols and isocyanates. And isocyanates are very reactive compounds. And this reaction occurs actually at room temperature. And if we will have time tomorrow in the afternoon, we will do this reaction as well in the lab. And quite often these polyurethanes are used in a applications where porosity is needed. So quite often polyurethanes have porous structures. And they are used for instance, for bedding, for pillows, and things like that, like this. And how this porous structure is produced. Of course, it can be in a different ways, but one of them is to add water to the reaction mixtures. Water reacts with isocyanate, produces carbamic acid, and this carbamic acid is not stable, decomposes to amine and carbon dioxide. And because this reaction of polyol and isocyanate is rather fast, this carbon dioxide remains trapped in the structure. So that's how about polyurethanes. And the last polymer I'm going to talk today is polydimethylsiloxane. Polydimethylsiloxane is a member of inorganic polymer. So this material does not have a carbon backbone like all other polymers you have seen today. The properties of dimethylsiloxane is that can be deformed and can recover. Polydimethylsiloxane can recover the shape very easily. It's chemically inert and it's good thermal isolator. So can be used also for applications for heat isolation or encapsulation of electronic products. So also in this case, I have one video. That's about it, yes. And the last slide is comparison between step growth and chain polymerization. Okay, that's at the end. Okay, sorry. So for chain polymerization, growth occurs by addition of one unit at a time. So only one unit is added at the end of growing chain. It means that monomer concentrations decreases steadily throughout the polymerization, while in step polymerization, any two unlike molecular unit can be added. So as a consequence, monomer disappears early in the reaction, and polymer chain length increases steadily during the polymerization. While in chain polymerization, polymer chains are formed from the beginning of the polymerization and throughout the process. So in chain polymerization, we have long molecular weight already at the beginning. This chain length remains approximately constant throughout the polymerization, while in step polymerization, average molecular weight for the reaction increases throughout the polymerization, and high molecular weight are obtained at the end of the polymerization. As the reaction for chain polymerization, as the reaction time decreases, polymer yield decreases, but molecular weight remains about the same, as we already mentioned. In step polymerization, high extents of reaction are required to obtain high chain lengths. In chain polymerization, reaction mixture contains almost only unreacted monomer, polymer, and very little growing polymer chains. While in step polymerization, reaction system contains various stages, chain lengths of products presented in a calculatable distribution. So that is comparison of these two polymerization mechanism. Here is another video about production of polyethylene. It's rather old video, but with nice presentation. That's all from my side for now. Any questions?
Thank you, Mark.
Yeah.
You mentioned some inhibitors for unwanted polymerization during storage and transportation. What
Yeah.
would be the maybe most common used inhibitor in what aggregate state?
Usually are different kinds of hydroquinones are usually used. And for instance, in styrene, we use in the laboratory, we remove these inhibitors with filtration through the aluminum trioxide. But in the industry, they usually do it with with distillation. Yeah. But of course, here we have to be careful with the temperature so that we don't go over certain temperature to start the polymerization.
Yes.
Yeah. Yeah.
It's removed only if it's really necessary, otherwise you just add more initiator and
Yeah. Okay. So, thank you.
We're gonna discuss.
To all the participants, thank you for being with us. And now is lunch break, and we will. Sorry. Yeah. Yeah. Till 2 o'clock. At 2 o'clock, we will continue in the lab.
We're here.